So let's begin by talking about collisions, which is chapter 10. In chapter 10, we have collisions. So let's consider the conditions for collisions, which is that in collisions, that the time duration is very small. This is a very fast process. So therefore, we can say that delta t is approximately 0. And also, since the time duration is very, very small, all external forces acting on the system has only a very, very short time duration, so that the influence of external forces is virtually 0. And so that those external forces can be the normal force, frictional forces, or gravitational forces. So the outcome of these conditions for collisions has an effect on the momentum principle and also the energy principle. So let us first look at the impact of these conditions for collisions on the momentum principle. So since we say that the time duration delta t is very small during collision, and also the external forces are virtually, the influence of the external forces are virtually 0 during collision, then we can apply the momentum principle in this way, since the momentum principle for delta p is equal to F net delta t, where F net is virtually 0, delta t is very small to be virtually 0, so therefore the change in momentum of a collision is 0. So we can write that the initial momentum is equal to the final momentum, meaning that the momentum is conserved. So this applies to all types of collisions. And then now we want to make the distinction between two basic different types of collisions. We can categorize collisions into two types. We have elastic collisions and inelastic collisions. So in elastic collisions, there is no generation of thermal energy, so no heat is produced, and there's no deformation. And in inelastic collision, you will see that objects can deform, heat can be produced, and objects also stick together. So that means that there is an impact on the types of energies created when we compare elastic and inelastic conditions. So let's write the energy principle to describe collisions. So if we have kinetic energies, we have a change in kinetic energies and change in potential energy, which because the external forces are 0, so therefore the change in potential energy is 0, so therefore there is no change in potential energy in collision. But we do have a change in the internal energy of the system. So this is for inelastic collision, where there is a change in the internal energies, such as heat or deformation. But if we have an elastic collision, there will be no change in internal energies, and kinetic energy is conserved. So therefore, in an inelastic collision, kinetic energy is not conserved. But for both types of collisions, whether elastic or inelastic, momentum is always conserved. So knowing this, let's move on to the clicker question. Let's look at the clicker question. So in the first clicker question, it's asking, what is the change in momentum when we have a ball colliding with the wall? So we have a ball colliding with the wall, and it initially travels with a momentum P initial to the right, then it collides with the wall and bounces right back in the opposite direction with a momentum of P final. So what is the change in momentum of the ball? So we can write, as from our earlier definition of the change in momentum, so we can write that the change in momentum is equal to P final minus P initial. And so we have the mass of the ball, and that's times V final minus V initial. So given that the mass of the ball is 0.1 kilograms, and taking note that the V final and V initial are in opposite directions, and V final is to the left, and so there's a negative 6, and V initial is to the right, and that's a positive 6. So therefore, we get a change in momentum which is negative 1.2 kilogram meters per second. So that's the change in momentum of the ball. So in the next example, we have a clay ball which is squishy, meaning that it can be deformed, and it collides in mid-air with a baseball. So we have a squishy ball colliding with a non-squishy ball, which is a baseball, and it sticks to this baseball. So if you look at this example, you will then see that the ball sticks. And not only that, the clay ball would be deformed after it sticks. So which equation then describes this collision? So that we can write, based on the momentum conservation during collision. So initially, we have the clay ball, which is the momentum of the clay ball, and the initial momentum of the baseball. And in the final state, we have the total momentum of both. So therefore, we have the correct answer would be that the final momentum of the combined objects is equal to the initial momentum of the clay ball plus the initial momentum of the baseball. So therefore, this shows that momentum is conserved in both elastic and inelastic collisions. So this would be an inelastic collision. So what happens to the kinetic energy of this collision? So how would you then describe the kinetic energy of this collision? So it's the same scenario with the clay ball colliding with the baseball. And there is deformation and they are stuck together. So this is an inelastic collision. So how would you describe the change in the kinetic energy? So we know that in both elastic and inelastic collisions, the total energy of the system is conserved. Right? But when you have an inelastic collision, in this case you have deformation, and they are stuck together. So then we introduce an additional term, which is the internal energy. So the internal energy of the system is changed. So in an inelastic collision, we introduce a new term, which is that the change in kinetic energy is accompanied by the change in internal energy. And since the total energy of the system is conserved, and that's equal to 0. So then for this type of collision, we can write that the final kinetic energy plus the final internal energy is equal to the initial kinetic energy plus the initial internal energy, and therefore the change in internal energy, and that's equal to the difference between the initial and final internal energy, and that's equal to K initial minus K final. So since thermal energy is generated, for example, so that means that the K final must be less than K initial. So it means that a fraction of your the fraction of your initial kinetic energy is transformed into energy of heat and energy of deformation. So let us look at the next example, where you have an example of a bullet of mass m traveling at a very high speed v, and then it embeds itself into a block of mass m, big M, and that is sitting at rest. So the block is at rest on a nearly frictionless surface. So what is true of the system of the bullet and the block during this sort of collision? So first of all, we need to recognize what type of collision it is. From the description, we see that they are stuck together because it's embedded. And also, heat must be generated because the bullet is traveling at very high speed and embeds itself into the block, and so that means that the block heats up. So this type of collision is classified as inelastic. So then again, we can write the conservation of energy principle to include a change in kinetic energy of the system and a change in internal energy of the system, such that K final plus internal energy final is equal to K initial plus internal energy initial, so that the change in internal energy is equal to E internal final minus E internal initial, and that's equal to K initial minus K final. Right, so since there is a positive change in the internal energy, so that therefore we can say that K initial, right, is more than K final. So that means that the final kinetic energy of the system now is less because a portion of the initial kinetic energy is transformed into heat. So let us now consider the scenario where we have two rocks. So in this question, we have two rocks colliding and they stick together without rotation. So here are the masses and initial velocities of the two rocks. So what is the vector velocity of the stuck together rocks after the collision? So to solve the first part, we consider that momentum is conserved in the system, right? Because this is clearly an inelastic collision because they're stuck together. But momentum is conserved, so then we can now write the momentum principle where P initial is equal to P final. So initially we have the momentum of the first rock with M1 V1 initial plus the momentum of the second rock, which is M2 V2 initial. And since they're stuck together, so we can write M1 plus M2, and then they have a final velocity of V final. So if we rearrange this equation, we get V final is equal to M1 V1 initial plus M2 V2 initial divided by M1 plus M2. So since these are vectors, we can stick in the numbers, and that's equal to 15, 10, minus 30, 0, plus 32, 15, 12, 0, divided by the combined masses. So that gives us a final answer of 13.4 minus 1.4 0 meters per second. So that is the final velocity of the combined masses after collision. So if we continue with the next part of this problem, which is that to calculate the increase in thermal energy of the rocks. So since we have identified this to be an inelastic collision, we can write that the change in internal energy is equal to the final internal energy minus the initial internal energy, and that's K initial minus K final. And so then we can now write the combined initial kinetic energies and subtract that by the final kinetic energies. So these two rocks, they stick together, so we combine the masses and with the square of the final velocity. So if we plug all these values in, so we have half these are vectors, right? So we have to do that. That's the combined mass. Then we have the vector result of the final velocity. So this gives us a final change in internal energy, which is the thermal energy of the rocks of 9,138 joules.